Let me spotlight myself. Ah. You guys doing all right out there? Next week is Thanksgiving. I don't know what that means for you necessarily, but at the very least, it means a bit of a break. So that'll be nice. I'm not sure if you guys realize that if you look at the homework sheet, you can tell that I actually give us Wednesday off also next week. I always do that, even now, because if you're going to travel, you're probably going to travel Wednesday. So I might as well give you Wednesday off. It's a fringe benefit. It gives me the day off too. So, hey, let's see. Okay, here we got a question. Good. Number 18 in 10.3. Okay, let me switch screens here. Pow. Pow. Okay. So 18, oh crap, I gotta set this up, hold on. Dadgummit.
Bluetooth mode.
Yeah. Bluetooth.
Bluetooth connected.
Thank you. So this dude here, right? Y equals 4x squared, and it says, convert this to a polar equation. So, oh, what is happening? Are you doing okay? All right, there we go. Sorry, all of my technology was flipping out for a second. So guys, help me out. What are the conversions for rectangular to polar? Why are they really, really, really nice? What is X in polar?
R cosine theta.
Isn't that crazy? And if you know that cosine likes X, you know, if you know SOHCAHTOA, they ain't gonna help you out worth shit. But you know that cosine likes X, so that makes complete sense. So of course, Y is R sine. That's crazy. So when they asked you to convert Cartesian to polar, just replace the X with this and the Y with this. So I don't know, did you do that and then you weren't sure where to go from there? But the answer you got was weird. Oh, okay. All right, well, watch. All right, let's see. What the hell? So if I replace Y with R sine theta. Oh, okay. And then I replace X with R cosine theta. Is everybody cool there? So, because it was Y equals 4X squared. So Y equals 4X squared. Bam. And then I can do a little tiny bit. And then what's one more thing I can do? Look what I can do. One more thing I can do. You can do a couple things, but I'm really just one more immediate thing. Anybody see something that happens?
Divide by R.
Yeah, kill one of the R's. So you get sine theta equals 4R. No, Jeff, you killed, that's right. You killed the other guy. That guy's still there. It's all right, Jeff. And then, I mean, you could solve for R and it looks kind of gross. I don't know if you did that. That's fine too. Yeah. I mean, if you solve for R, it's just going to be, let's see, you'll get 1/4 sine theta over cosine squared theta. And then you could bring the sine in one of the cosines and make it tangent. And the other cosine is going to become secant, right? Is that all right? Yeah. Okay. So don't freak out if it looks weird, man. So what I'm saying is sine over cosine is tangent. 1 over the other cosine is secant. Kabam. Kabam. And think about it. Obviously, what is this in Cartesian? What is this in rectangular coordinate system? What does that look like? What does that look like? What is that? What is it? What's that look like? What's this look like? Does anyone have a mic? Anyone? Nobody has a microphone. What does that look like in Cartesian?
Parabola.
What's that look like? Parabola. All right. So, and this is definitely not circular, right? It is curved, but it's not circular. So I should expect the equation to be a little interesting for a shape that's not circular when my coordinate system is based on circles, right? So that's okay. It's going to look a little weird. You guys with me out there? Maybe. Okay. Maybe. Okay. All right. How's everybody else? Any other questions? That was 18 and 10-3. Okay. All right. All right. No questions? Everybody, everything else is good? All the other homework is beautiful? Fantastic. No issues at all. Okay. I'm an optimistic fool. I'll take that as a good thing. I mean, if you guys are all perfectly fine, we're going to get into the last section of chapter 10. You know, like, yeah, bring what? Come on. 2020 has put us in this mindset of, sure, more shit. Why not? Just pile it on top. I'm under a lot of shit already. So just keep on piling this shit on, Jeff. All right, I'll do that. That's my job. Before I get into the last section. So we only have one more section of chapter 10. Last time we did do at least one example of a parametric graph, I believe. And just to show you, if you haven't looked at the homework yet, they do a pretty good job at the beginning of not dangling you out there on your own. So they give you values of t, because sometimes the hardest thing about parametric equations are, how big of a step can I take for the t value? I don't know if you guys remember. Remember we had to do that one value that was in between just to get an idea what the curvature looked like, because it wasn't high enough resolution. Does any of this not make sense? The smaller the step size in my inputs, the better resolution I get in my graph. But here they kind of give you, okay, fantastic. So I just do this and graph it. Went fantastic. And then down here, they don't. Oh, shit. So here you've just got to give yourself some values and see what happens. I would do like some negatives and some now here, obviously, you kind of have an inherent domain for your t, right? Do you guys see? So, okay, just pay attention to that. Yeah, all right. And look at 17. Let me say something. Look at 16, 17, 18, sure. Let me say something about those. Those are closed. Does somebody understand what that means? Those are closed. Those aren't open. Those are closed. Like a circle is closed, but a parabola is open, right? Because it goes off to infinity in some direction. These, neither x or y are allowed to go to infinity, correct? So they are somehow going to do one of those weird little things where they make a nifty little thing inside of a certain area. We saw that one the other, we sketched out that one the other day that I said looked like the goldfish that ate Manhattan, right? All right. Maybe. These get kind of funky. I'll let you have fun with these. If I can't remember if I think I maybe assigned one of those. Yeah, they don't say up here. Yeah, right here. Good. When they say include the orientation, what does that mean? Does somebody remember what that means? We did it with the ones we graphed yesterday. What does that mean?
Is that the arrows?
Good. I like it. I was going to make a joke about. Anyway, I won't. So whenever they say include the orientation, that's what you should always do, is include the arrows. That kind of tells you what direction. So the beautiful thing about parametric equations is they inherently are useful for trajectories because they have a built-in variable, the parameter t, that could be thought of as the time parameter. So you've got this built-in, so if I just had a function y equals x squared plus 4 or something, I wouldn't know when the thing was at this point. But if it's defined parametrically, I could look at the t value at that point and I know when it was there. Okay, maybe. So those are a beautiful immediate use for this is trajectories of moving objects. Sure, it's following maybe a parabolic arc, but I want to know what time it's at each of these positions, right? Okay, maybe. And of course, this extends to 3 dimensions, and that makes it even more fun, but we're not going to go there, unfortunately. Let's see. Here they give you domain for t, which is always nice. And then this one I think I assigned like 36 and 39. It was a little bit evil because you do have to kind of look at some of these to get the idea for number 39, but have fun with that. All right, I just want to make sure I don't think there was anything too freaky in here. Here's where you can use the graphing calculator and just make sure you put it to parametric mode. All right, and then here, this looks kind of familiar, right? Except the one we did, it was only bounded in the x direction. It was unbounded in the y direction. That really looks neat. Okay, all right, there's another kind of fish. All right, enough of that. All right. So let's get into section 10.8. And the funny thing with section 10.8, I'm going to do some stuff on the board tonight because I'm tired of sitting on my ass. I think I've got this set up. Yes. Oh, maybe I should turn off my fractal background. Oh, God. Okay. All right. So I don't know where that leads. Let me turn that thing off. Oh, Zoom updated, and now it takes it forever. Oh, here we go. How do I turn this off? Oh, yeah. I got to go up here. Yeah. Bam. Okay. So, the immediate reaction you might have to this is we've already done this, and it's true. We've done the component parts that go into vectors. We've done them, which is beautiful, which is why it's at the end of chapter 10, because it all leads up to this. All right. Oh, do I need a new pen? Man, I don't know if you work. All right, let's find out. So here's the idea. So let me do it this way first. It's interesting teaching this because I never know where to start, but let me do this more visually first. So a vector is really just something like this. It actually doesn't go forever, but the arrow just tells me orientation, just like with parametric graphs. It has an initial point. Oh, crappity do that. Do you know how to spell, Jeff? And it's got a terminal point. Sorry, this is about to fall off. God dang. Jeez. All right. And the way we name these, the most basic names for vectors, sort of like names for variables can be a lot of different things, but the most basic variables are x and y. The most basic names for vectors are u and v. So I can call this vector u, and it's got this little symbol over it to tell me that's a vector. In a book, they'll very often put it in bold font. It's really difficult to do bold on a board, so we made this little symbol for when we're writing these things out by hand, right? And that's just going to go u. All right. So there's two parts, two identifying aspects to a vector. And these are going to feel very familiar. There's the magnitude and the direction. So magnitude is really another name for length. And direction, this is going to be interesting. Direction really is about the angle, but there will also be a direction vector that we're going to talk about later. But for any given vector, it's going to have a length, a magnitude, a length, and a direction. All right. So something to realize about this. Let me do this. Let me put this over here. This is always a question about space. So if I have a vector that starts at the origin and ends at a point, I would call that vector x, y. And see how the symbols on the outside look like inequality symbols? So that's what tells me it's a vector and not a point. Get out of there. So the point is x, y, like that. But the vector means it's not just the end, it's this whole thing. That's the vector. So that's what this represents. Okay, I like it. I like it. Can somebody tell me, how would you find the magnitude of that? And the other name for magnitude is length. How would you find the length of that? You know this. You know how to do this. How would you find, let me say this a different way. How would you find the distance from here to here?
Use the distance formula.
Use the distance formula. I love it, right? And we actually know something better about this from our discussion about complex numbers. So the magnitude is actually, so let me call this vector v, because I already got u over there. Let me call this vector v. So the magnitude, this should look very familiar. I use this absolute value notation, but we call it magnitude. Just like we did with complex numbers in the complex plane, right? So in this case, this would just be the square root of x squared plus y squared. Amazing. And then the angle, the direction, let me put that in there. So this is the part that feels like, why the hell did they make a whole other section for this, Jeff? This is polar shit. Well, hold on, right? I don't, nobody's saying that. That's my own imagination, but just to head you off if you're thinking that way. Well, how would I figure out the direction, the angle?
Do you use like side angle side?
No. Don't have to think that much about it. It's exactly what we did with polar form. How did we figure out the angle? We took the, what do I know about this? I know this is x, I know this is y. So how do I get the angle?
Inverse tangent.
Yes. All right. So I warned you about this. This is just the bare beginning. So don't think, well, we've done this shit before. Although some of you guys would be like, oh, please let it stop there. We've done that shit before, but don't, yeah, well, don't. It's too bad. We're not going to stop there. All right, so this is the very, very basics. These are the two main things we can talk about with vectors. That's how to find them, right? I like it. Now, here's the real, here's an interesting thing about vectors. If I took that vector v, I could pick it up and put it anywhere I wanted to, and it's still vector v, even though its initial point and end point is now different. But let's say this initial point is 2, 3. And this end point is, what are you going to do, Jeff? There you go, buddy. Good job. What's it look like? Maybe make it like normal scale. That would be nice. 1, 2, 3, 4. 1, 2, 3, 4, 5. So 5, 5. I like it. So I want you to be very careful. What would the name of this vector be? What the hell do I mean by that? The name of this vector is this. XY. That's the name of the vector. I can see the name of the vector as the point if that was at the origin. So let me think of this a different way. How much would I have to move this point? Some of you guys already know this, but I just want to do this. Just let me do this. How much would I have to move this point to get it back here? I'd have to move it down how much?
3.
And then back 2, right? So if I do the same thing to this, move this down 3, move this down 2, I would end up with the point that it would end at if I did pick this up and move it back. That's very simple. Is everybody sort of with me? So I'm almost certain that some of you guys knew that was going to be the way to do this. So in general, I can do end. So it's always got to be, let me see if you guys are cool with this. It's always got to be the terminal minus the initial. 5 minus 3. Oops, I'm doing this kind of backwards, but too bad. And 5 minus 2. So this guy's name would be 3, 2. What would happen if I did that backwards? If I did 3 minus 5 and 2 minus 5, I'm going to get negative 3, negative 2. But where's that vector? That's here, pointing the other way. So it's kind of like the reverse of this. Okay, let me stop. Let me stop. All right, so far, this is not that big of a step from stuff we've done. This is actually the first new thing. We never really talked about picking this shit up and moving it around. When we did R and theta, it was basically always in relation to this. Now we can move this shit around, thank God. Now we got a little more flexibility. Okay. Let's see. Oh, that's right. I got a little ahead of myself. That's fine. Blah, blah, blah. Here we go. Okay. Some cool shit coming. So what we've done, this is something you don't even realize yet. We have defined another level up from just numbers, right? So you know the numbers 1, 2, 3, 4, and all the infinite numbers between those. Whoop-de-doo. We've defined elements that are each like a number in itself. So we have to rediscover, how do you add these? How do you subtract these? How do you multiply these? Is anybody at all with me? So when you create numbers 3 and 4 and 5, you know, you're sitting around 4, 5, 3, and like, oh, and then you got to think, what can we do with these things? I had 5 rocks, and then Ugg came over and stole 3 of my freaking rocks. I got to come up with the idea of subtraction while I go beat his head and take my rocks back, right? Sorry, it was caveman times. It's bad. Sorry, it's just the way it is. I could have done a Game of Thrones thing, but oh. So if I have 2 vectors, so U and V, there they are, just hanging out in space. And I want to figure out what U plus V is. Become a normal, there we go. I want to figure out what that is. Let's see what that looks like geometrically, and then we'll talk about what it means algebraically. So geometrically, what I would do, and here's the idea. Let me see. This is really interesting, trying to figure out what order I want to show things to you. One thing that vectors are used for example, is wind. Have any of you ever looked at a wind map? All right, and I've got a link to a wind map. I might show it to you later. But basically, if on the map you see this, that means it's pretty weak wind blowing to the, you could do it, Jeff, southeast. But if you see this shit, then holy shit, there's big ass gust coming from the east to the almost west, right? You guys kind of with me? Those are vectors. The length represents the strength in this case, right? So they could be force vectors. They could be, what else you got, Jeff? I don't know. Okay. So it kind of makes sense. If these are sort of working together, in which direction are they working together? I don't know if you guys are going to be with me or not on this. Think north, south, west, and east. Yeah, aren't they? They're both working together that way. But how are they working just different from each other? This one wants to go up and this one wants to go down. So I can think of this as two people pushing on a box or something, and one guy's pushing it this way and the other guy's pushing it down that way. It is going to move. Which way is it going to move, right? Which guy is pushing on the box harder? I think I made one. Yeah, I did. Okay. One's a little bit
I'd say
longer.
vector U.
Yeah, U's pushing a little bit harder. So let me see. So let me see if I can copy this down pretty well. There's U. And there's, geez, Jeff, you're fine, dude. And there's V. So what I do is I line them up tail to head. And U plus V will be this. So see, now look, compare it to U. That would take this down. It would move it down a little bit, but it would also lengthen it because they're working this way together and this way differently. So visually, that makes sense. Okay, maybe. So what about U minus V? Well, here's the weird thing about U minus V. So one way to do U minus V, oops, we do this in the same color scheme. One way to do U minus V is to have, you actually do this. U plus negative V. Same thing. So then you can use the same idea as addition. So here's U. Oh, this is going to suck, Jeff. Let's move that. I got to think ahead. Here's U. It's a little too long. You're Jeff, really? It doesn't matter, dude. All right. And here's V, negative V. So it's going to go back there. It's got to be a little longer, Jeff. Really, dude? Yeah, it does. It's not perfect. That's all right. And then, so this is U. This is negative V. So if I add those, I'll get U minus V. It's all right, buddy. There you go. Yay. Okay, now visually, it's kind of sucky. You can't be very detailed, obviously. This is why I need some help algebraically. But before I do the algebraic part, I want to show you a way to do this visually all together. So what we do is we do this. Here's U. And let me draw another U. I got to keep this straight. Oh, this is why I normally don't use so many colors. Here's V, pop, and let me make a parallelogram. V and U. Now the only way I could keep calling this U and this V is they must be the same length and the same direction, correct? I can't just, in a single problem, I can't give the same name to two different entities. So these are the same vector, just displaced. These are the same, just displaced. Here is U plus V, same answer we got here, right? There's U plus V. Cool. And here is U minus V. Same answer we got there. All right. But again, the visual method is not the most, the best way to get the actual exact answer to something like this. So here's something kind of cool. I mean, this is something you might have expected is going to happen. This kind of only makes sense. And let me see, do I want to do that first? I figured out earlier the way I wanted to do this. Maybe not. Oh, that'll come later. Okay, we'll do that. Yeah, okay, I like it. So if U is something like, let's say, 2, 3, and V is something like, see, I'm trying to think of 2, 3, and this would be maybe like 1, -1. U plus V is actually, of course, just, you guys might have seen this coming. 2 and 1 is 3. 3 minus 1 is 2. You just add the components together. We're going to look at this in a different way in a minute, but I'm almost certain some of you guys kind of felt that coming. It kind of makes sense because this and this are acting in opposite directions, right? This piece of it, but this piece and this piece are acting together. So the X pieces added to each other, made each other longer, and the Y pieces are acting in opposite directions, so they subtract. It only makes sense. So obviously, what would U minus V be? It would be 2 minus 1 is 1. 3 plus 1 is 4. And that kind of makes sense from the visual here. 1, 4. I like that. I don't know if I want to put too much on there. 1, 4. That looks like it might be 1, 4. Okay. I like it. Maybe, maybe. So that's not ground shaking. But I do want to immediately on the heels of that do this. This is the part that I wasn't sure what order I wanted to do it in. How we all feeling so far? You guys all right? So this is the algebra behind this visualization of these. And again, this is not very useful if I want to know exact answers. If I just need some idea, I can do this real quick. Okay. Now here's something interesting. So let's say I've got let's make another vector. Let's say 4, -5. This is the vector 4, 0 plus 0, -5. This is the vector 4, 0 plus the vector 0, -5. Is everybody cool with that? And here's the really, really cool thing. This only makes sense. I'm going to give the only vector that gets this symbol, right, little I hat. The only vector that gets that symbol is the vector that points along the x-axis. That is a unit vector in the direction of the x-axis. Is everybody cool with that? Because of course the point 1, 0 is there, so the vector 1, 0 is there. It's the unit vector, and it's so perfectly set up. So what is this? How can I rewrite this then in terms of I? It would be 4 times I. If I put 4 I's in a row, now I sound like Game of Thrones. 4 I's in a row, tack them up. That makes 4. It's crazy, and I get out to 4, 0. And of course, what would this be? It wouldn't be that. It would be what? Oh, you don't know yet. What do you think I call this vector? Knowing math people are not very creative. That one's I. That one's going to be. No? What do we like to do, math people? Well, one variable is x, the next one is y. How about A and B? If this is I, I'm going to call that one J. Right? We like to go in order. It's just crazy. It's something about us. If we went into 3 dimensions, I would have I, J, and K. K for the z-axis coming out of the board. We're not going to do that. We're going to stay flat. Okay. All right. Maybe, maybe. So then this would be minus 5j. That's another way to say this vector. I like it. So now it makes even more sense why we add vectors the way we do. So if I have a vector, if I have this vector u and I have this vector v, -7, 6. So that means that v is, can you guys see that all right? Yeah. -7 I hat plus 6 j hat. Is that cool? All right, I like it. So then if I want to do u plus v, and I look at it in terms of I and j notation, this just becomes freaking like terms. You can do it, Jeff. There you go, buddy. Right, now it just becomes like terms. I get the i's together, and I do the j's together, which if I want to put it back into this format, it would be -3, 1, which is what I get if I do 4 minus 7 and -5 plus 6. Okay, I like it. It all comes back on itself. That's always nice. Kick ass. All right, let's see. Oh, yeah, now we're getting to the really neat stuff. So let's focus on, I'm going to erase this down here. I want to focus on this bad boy for a minute. All right, I'm going to erase all this here. I'm going to use a better pen. Sorry, little dude. So this vector is 4, -5. So it does look like this. Is that a unit vector? What's your gut instinct say? Is that a unit vector? Think like unit circle. And I said unit vector earlier. It has to be a vector that has a length of what? A unit vector. Unit circle has a radius of what? The unit circle has a radius of, am I muted? Am I still going? Is this thing on? Anybody? Unit circle? Unit circle. Has it been that long? Nobody wants to say? Did you guys all communicate beforehand and say, don't respond to any of his questions? Let's just see how crazy we can drive him. One, anybody? One? Was it too easy? You guys are like, I don't even want to answer that question, man. Thanks. Doug. Doug is like, he got it. He made it. All right. What is the length of this vector? Can somebody figure out the length of that vector, which is also called its pop magnitude? Anybody get that reference? Pop? No? Okay. So I want to know the magnitude of this bad boy. That would just be the square root of 16 and 25, right? Okay. 16 and 25 is 41. Now watch this. I want to get the unit vector that points in the direction of this. This is that directional vector I talked about earlier. So the direction of a vector is the angle. A directional vector is a unit vector that points in the direction of the vector. Oh my God. So many words. You guys sort of with me? These are crazy useful. I and J hat, the hatted ones, they are crazy, crazy useful because I can build other vectors with them. But I can extend that idea. I can get any component vectors, any unit vectors, also called component, because we can build with them, pointing in any damn direction I want to. Find a vector pointing in the direction you want. How do I make this guy have a length of 1? I take him and I divide him by his length. Does that make sense? Maybe. So if I take this and divide it by his length, I get this funky ass thing. 4 over the square root of 41, -5 over the square root of 41. Take a minute and figure out this guy's length. Do it. Actually do the work. Don't just go, well, it's 1 like you just said. No, do it. Figure out this guy's length. The same way I figured that out earlier. Figure out this guy's length. Some of you guys are just staring at me. It's not going to work that way. Or maybe it will for some of you guys. You just do it in your head. That's beautiful. Some of you guys might see what's going to happen. You're like, I already see what's going to happen, Jeff. It's not very interesting. I'm sorry. So the length of this little vector I've created will be the square root of this p squared plus this p squared. Some of you guys see how this is kind of silly maybe. Of course it's going to be 1 because 16 plus 25 is frickin' 41 and the square root of 41 squared is frickin' 41 and the square root of 1 is 1. Yeah, okay. But now you know how to take any vector and create the unit vector that points in the same direction as that vector. So here he is. I don't know. What is 4 divided by square root of 41? It's like 2/3, and then the negative 5, or I don't know, it's going to be 5, 6. So maybe, so it looks like, yeah, right there. There it is. There's our little unit vector. There's that guy, that little beep, beep, beep. So if I call him, oh shit, if I call this guy, what, Jeff? I'm going to call him M for whatever reason. Then another way to write this would be the square root of 41 times M. Let me stop there. Does anybody not get that? I might have went one step too far, but it's okay. I do that. Because this guy points in the right direction, and then this guy just makes him become that long. So of course that's another way to write this. Okay, maybe. So the angle part, the directional part, is part that's normally harder to get. To get the right length, I just multiply or divide it to get it to be the right length. Yeah. Okay. There's a little something inherent in a couple of things I've done. Let me make it really, really explicit. If I have this vector, what do you got, Jeff? 2, -3, sure. What is 5u?
Would it be 10, -15?
Isn't that crazy? Because the idea is 2, -3, and what do I do to get five of these? So I just put another one of these and another one of these and another one of these. So it's going to be 5 times in that direction and 5 times in that direction. So it's just going to be 10, -15. That's insane. Does anybody see how the idea of slope is in there too? Slope doesn't give a shit how big the step is. You take this big of a step, you got to go. You take this big of a step, you got to go way the shit over there. Right? That's all that's saying. All right. Good. I'm trying to break some of you guys out of here. Like, we're in that time of year. Let it end. I understand. All right. And you know, I could, what would this be? Ooh, what would that be?
One -3/2.
Yeah. Okay. So none of that. This is called scalar multiplication. Has anybody ever heard the word scalar before? This sounds like, I don't know, sounds like some kind of medical term, or I have no idea. But we use the word scalar when we introduce the idea of vectors. Does it make sense for me to say this is a two-dimensional object? Do you understand that? That is a two-dimensional object. Maybe? No? Okay, good, because it has an x component, a y component. Scalar just means one-dimensional object, meaning a constant, meaning a number, right? Okay, now, so we've talked about how to add vectors. We've talked about how to subtract vectors. We talked about scalar multiplying. So that's taking a vector and multiplying it by a number. How about multiplying two vectors together? How about that, Jeff? What the shit would that be? Oh boy. All right. This one is exciting. I think you might be able to imagine that the process of multiplying two vectors will not be simple. Actually, let me say this a different way. It's not simple in the sense that there are multiple ways to do it. And I don't just mean many ways to get to the same answer. I mean, there are multiple definitions of what vector multiplication is. And we're going to just talk about one of them. I'll tell you what they're both called. We're going to, this is the one we're not going to talk about. This one called the cross product. And the result of this is another vector. So this is a vector times a vector. You can do it, Jeff. Equals another vector. And that's the actual symbol we use. The one we're going to talk about is called a dot product. And remarkably enough, get this, there's a cross product and there's a little cross in there. Holy shit. Dot product, there's a little dot. And now you guys understand why we have X multiplication sign and we have a dot multiplication sign. Holy shit. This bad boy results in a scalar. How do I want to represent that? C. Scalar, constant, freaking number. There. Okay. So let me show you an example of something we already know. If I have, here's one vector, that's the vector 3, 0. Here's another vector, that's the vector 4, 0. Those vectors actually truly represent the number 3 and the number 4 in a very basic sense. So what do you think I get when I do 3, 0, dot 4, 0? 12. It's insane. All right. The weird shit comes in when they don't agree with each other, right? When they line up with each other, it's just like our normal multiplication. Let me be very careful how I say this. When they line up with each other along an axis. I mean, if they line up with each other at an angle, that would still be some weird shit. And what I like to do, let me see if I can get you guys to go with me on this journey. I like to bring back, so this is, yay, okay. And really, let me come back to these guys for a minute. And here's the idea of dot product. Dot product is a measure of how much the two vectors agree with each other. What the hell does that mean? So if I have this vector and this vector, the dot product is going to be the maximum it could be because they completely agree with each other in what direction they're going. Sort of like adding two vectors if we add the parts where they're going to get in the same direction, but not quite that way. So what do you think with that definition? Very vague definition, I understand. What do you think about the vector I hat and j hat? What would their dot product be? If this is maximal, because they totally agree with each other, do these agree with each other at all? Do they have any component going in the same direction as the other guy? No. So what do you say? What's your gut tell you that the dot product should be?
0.
Heck yeah. Shit. You're like, damn, I'm not used to my gut being right. Do you know how long it's been since my gut feeling was right? I understand. All right. But that's almost too beautiful to believe. Now stay with me. This is where things get really kind of cool. I like to teach this order because it makes a little more sense, especially because I think most of you guys should get this intuitively. If I tell you, and this is true, the dot product does talk about how much does one vector lie in the direction of the other vector. That's what we can eventually use it for. Sort of like, let me show you this, and then I'll get into the specifics. If I have a vector U and a vector Jeff, buddy, there you go, buddy, vector V, I can use the dot product to see how much of U lies along V. It would tell me what this is. I like it. In fact, we're going to come back to this here in a minute. I could do it right now. No, I want to do the other one first. We'll come back to that in a minute. I'm going to recreate that in a bit. I'm going to probably make it bigger. So let me do this. So a really big thing for you guys to know. Oh, by the way, Jeff, you always forget the little hats. This is 0. I don't know if you guys would understand. What do you think I dot I would be? What is their magnitude? And by definition, what's the magnitude of I hat? It's a what kind of vector? This is helping. Sorry. Does anybody remember? Starts with the letter U.
The unit vector?
Unit vector, which in the word unit normally means 1. I like it. So this has magnitude 1, magnitude 1. They lie in the same direction. The answer is 1. So this is the equivalent of 1 times 1. And of course, so what would j hat dot j hat be?
1.
1, yes, kick ass. Kick ass. Oh, by the way, are you guys understanding? What would j hat dot I hat be? What if I turn it around? Does that save it? Does that save its ass? Do they agree now? So of course it's still too bad.
0.
All right, now watch. Here we go. So if I had to do this dot product, doesn't matter, Jeff. There you go. Look, make numbers up. Dotted with, make some more numbers up. There you go, buddy. Try another negative. Okay. One way I can do this, and then we're going to develop the shortcut, but let me do this the long way first. Let me rewrite this as 4i hat minus 3j hat, negative 2i hat minus 5j hat. Can you guys please FOIL that shit for me? So what does that mean? What is in the middle of this still is a dot product. So watch. 4 times negative 2 is negative 8. I hat times I hat is 1. Is that cool? So I hat dot I hat. Let me be very careful. So when you're talking about vectors, you will very rarely hear somebody say the word times, because like I said, there's multiple definitions of what multiplication means. That's not a pun I meant to do. Sorry. There's many ways to define multiplication for vectors. So I dot I is 1. So now if I move us, that's this. Now what if I would get here? 4 times negative 5 is negative 20. What's I dot j?
Zero.
0. And of course, here we're going to get the same thing. Negative 3, negative 2 is plus 6, but what j dot I is 0. And then negative 3, negative 5 is plus 15. J dot j is 1. So the components that agree with each other multiply, and the components that don't agree with each other at all, they have nothing that will work with the other one. So that's just 0. So I end up with negative 8 plus 15, 7. So what is the shortcut, Jeff? Please tell me there's a shortcut. Yeah. 4, negative 3 dot negative 2, negative 5 equals 4 times negative 2 plus negative 3 times negative 5. Because the cross stuff zeroes out, right? So you can just do component times component, get them together. Remember, the answer to a dot product is a number. If you get a vector at the end, you have messed up. Okay, I like it. Maybe. Now, I want to come back. So let me write this in general. Let me write the general definition of dot product this way. And then I want to come back to that picture I had up here earlier make a comparison, and then probably call it a night. Because we've done a lot of shit today. All right, let's see. I think everybody's got that. Okay. So here's the general definition. Okay, that's exciting. And that's why you end up with just a scalar, just a number. It's only got one component to it. Earlier, I said the idea. So let's say this is this is perfectly lined up. So this is the angle, stops it with the angle. This is the vector v, and this is the vector u. And what I want to do is the piece of u that is in the direction of v, the piece of u, it sounds like a song. The piece of u that's in the direction of v, those two will multiply. This other piece of u does nothing. It's not agreeing with this vector at all. Let me stop for a minute. We're still in the idea of dot product. Dot product's all about the things that agree with each other, multiply. The other stuff that don't agree with each other at all, die. They just die. Okay, I like it. What the shit is this? Let me bring the angle back in. How much of u is here? What is that? Now we're going back to nice, normal trig. You never thought you'd be like, oh, good, trig. What is that? What is this piece? You got the this and you got the this.
Would it be vector u times cosine of theta?
Kick ass. And let me be really careful here. This will be the length of u times cosine theta. I like it. Right, because then I want the length to make it like a side of a triangle. Is that cool? You guys all with me? So this is the vector, but when I want to use it, I want to use this like a side of a triangle. It's the length I want. That piece of u will multiply with the length of v. And that would give me the same result. So this is another definition for the dot product. U dot v equals this. Let me write it a little bit better. U dot v equals mag u mag v cos theta. I like it. Which I know I said that was going to be it, but too bad for you. I really want you to understand something. In order to set this up nicely, do you see how I laid v out across the x-axis, right? It doesn't frickin' matter. This could have been, I could take this and move it. If I take everything the way it is and just turn it around, none of the shit would change. It's independent of orientation. Sort of like law of sines, law of cosines. I don't care how the triangle's oriented, right? This feels very much sort of like a piece of law cosines, doesn't it? A little bit. I won't bring that back up. I'm sorry. But watch this. I promise. This is, what time is it? Sure. This is the last problem we do. We'll see if, no, I promise. If I do any more, you can leave. This is the last problem I'll do. What if u is 1, -4, and v is, what do you got, Jeff? Does it really matter? 3, 1. So let me do a quick little 1, -4. So there's u, 3, 1. So there's v. Ooh, it looks like it might be 90 degrees, right? From my crappy little, I'll bet you it isn't, but it looks like it's close. We're about to figure out exactly what the angle is using vectors. Can you guys help me out and do this? Figure out what that dot product is this way. Do that real quick. Don't worry about this. Do it that way. Somebody should be done by now.
I got -1.
Yes. So you get 3 - 4, -1. But isn't u dot v equal to this business? Right? Can you figure out, do I know what this is? Yeah, we just figured it out. Or you did. I stole it from you. Haha. What is this guy? Can somebody figure that out for me semi-quickly? What's the length of U?
Square root of 5.
No. Squared, right? You got a square.
17.
17, I like it. And then the length of V, be 9, 1, so it'll be square root of 10. Cosine theta, I can solve for theta, right? I can get the angle between those two vectors. Whatever orientation they are, I can always do this. Do the easy dot product for that side. Get this, I can solve for theta then. All right, so let's see, what would theta be? It would be the inverse cosine of -1 over the square root of 170. Is that cool? Get those together, divide, inverse cosine. And now I got to know. That looks very close to 90 degrees. Shit and a half, Jeff. Damn it. Darn technology. Oh, yeah, look at that. Anybody get that yet? That's kind of cool. Nobody's doing that with me? Anybody get that? Nobody cares. What'd you guys get? Anybody?
I got 94.399.
Yeah, we'll just call it 944. Pretty damn close to a right angle. I love it. I didn't do it on purpose, to be honest. That's why I got excited. All right, that's enough. I promised. No more after that. That's enough. That's some neat shit, though. I hope you guys possibly agree. We just created a new mathematical entity tonight, right? Vectors, and they have their own algebra. That is just so cool. And it's relatively simple. It's built on stuff we've already done, and you can immediately do some kick-ass cool shit with it. Okay, all right, that's enough. Let me know if anybody needs to be afterwards. Otherwise, you are free to leave. Let me know. Anybody need anything, or are you all good? I'm out of
No.
here then.
Thank
Oh,
you.
good.
I was just saying bye.
Bye.
Yep. Thank you.
Sure. Everybody else is good? All right, I'm alone now. Hey, future students. I'm in my Zoom room by myself. Okay, I'm leaving.